Hello and welcome to ECMath. Today we're going to be looking at the graphs and behavior of rational functions. Rational functions are any function of the form p of x over q of x, where p of x and q of x are both polynomials, which we've already learned about. So to be prepared for this section, I really would recommend you understand graphs of polynomials. And we're going to talk about sign charts, which is from section 2.7. So I'd recommend that you be familiar with sign charts. So the very first rational function we're going to look at is kind of the parent of all other rational functions, and that's 1 over x. And I should have written this as y equals 1 over x. So let's look at how this thing behaves. Well, to think about 1 over x, we really want to think about fractions. If x equals 1, then this is going to be 1 over 1, which is 1. So this is going to go through the point 1, 1. If x equals negative 1, then this is going to be negative 1 over negative 1. Sorry. So this is going to go through the point negative 1, negative 1. So those are kind of two critical points. But there's also some weird x's. So if x equals 0, then this is going to simplify to 1 over 0, which is undefined. So for our first time, because we have a rational function, we have something in the denominator, we have values that are undefined. Also, if we think about x being very big, then it's going to be 1 over something big. Well, 1 over something big is going to be very small. But if x is small, and when I say small, I mean between 0 and 1, then this is going to be 1 over small. Well, when you divide by something less than 1, you get something very big. And the closer to 0 you're dividing by, the larger the result is going to be. So there's just some ways to think about this. So here's what the graph actually looks like. We do have the points 1, 1 and negative 1, negative 1. And then the graph of 1 over x kind of curves like this between the axes. And there are arrows on both ends of this branch. That's one branch of this graph. But this graph actually has two pieces because we could also have negative x's. And those will go from the point negative 1, and you'll curve down like that. And over like this. And what's true about this graph is it never crosses either axis. So this vertical axis, we sometimes draw a dashed line here. And because when we plugged in 0, we were undefined, we call this a vertical asymptote. I think you've probably seen the word asymptote before, but in case you haven't, it's just a line that's not part of a graph that a graph gets closer and closer to. So it means getting closer and closer to. And you can have both vertical asymptotes and you can have horizontal asymptotes. And since this line towards infinity also gets closer and closer to 0, but never actually equals 0, then we also have a horizontal asymptote. A lot of our work with rational functions is going to be about finding and labeling the vertical and horizontal asymptotes so that we can fit the graph in, on, and around those asymptotes and where they sort of intersect. All right, so let's label some of the features of this graph. This is something we're going to do with rational functions all the time, just like kind of talk about where they are, what they do. All right, so holes. Well, we don't know what holes are. I'm just going to tell you, for now, there are none. We'll say no holes. X-intercepts. Does this touch the x-axis? No, so we're going to say none. And I'm going to say x and y-intercepts. We are generally going to be finding y-intercepts. This one, also none. Vertical asymptotes. That's this red line where the graph kind of bends out of the way. We always write asymptotes as the equations of the lines that they are. And so this is the line x equals 0. Remember that a vertical line always has equation x equals. And the horizontal asymptote is the line horizontal y equals 0. So these are just the basic features of the graph. And then the key points are 1, 1, and negative 1, negative 1. I'm going to add one more key point when we think about this graph, and it's the point that's not actually on the graph. It's the point where the asymptotes cross, 0, 0. So 0, 0 is not part of the graph. The asymptotes are not actually part of 1 over x, the equation. But when we're thinking about taking this graph and moving it around, it's actually really nice to think about where 0, 0 moves to. And that's what we're going to do in our first little section, which is all about transformations of this one graph. So let's take a minute and look at some transformations of 1 over x. And I want to actually challenge you right now to pause this video. And if you have this note sheet in front of you, try both of these problems, write it down, maybe use pencil, and see if you can do it. If you know about the parent function and you remember all your transformations from the last chapter, you can do this. So give that a shot and then come back in a minute and we'll go over it. All right, so the first transformation we're going to look at is 1 over x minus 2. Now, the first thing we have to do is identify what transformations have happened, and for 1 over x, this can be tricky. So if I really want to think about what the parent is. The parent graph is y equals 1 over x, and I want to look at what transformations have happened. Now, I'm going to put parentheses around this denominator. They won't give you that, but you can do that, and that's actually showing you that the transformation has happened to x before it became a reciprocal. And the reciprocal, the 1 over part is the function that's happening here, the main thing that's giving it that awkward shape. So this is really like when you have, f of x minus 2. That is, you're doing a transformation on the x. So this is going to be a transformation. It's going to be a shift. We're going to be very specific. We're going to say it's a horizontal shift. And it goes right 2 units. So we can actually draw this now. And I'm going to go ahead and do that, just looking at the parent. That's the easiest thing to do. So I know that 0, 0 is going to go to 2, 0. And that's going to be the place where the asymptotes intersect. So I'm going to go ahead and draw those in now. There's no vertical shifts here, so we're just going to do this. Draw those in. Then 1, 1 is going to go 2 over, so it's going to be at 3, 1. And negative 1 is going to go 2 over, so that's going to be at 1, negative 1. We've actually done everything we need to do now. We just have to fill in the rational function. So we have to obey the asymptotes. We're not going to touch those. We're going to squeeze the function in between those and just make it look like 1 over x, but it's been shifted over. It's usually easiest to start at those 0 points and draw both ways. It is important that you draw both ways. Sometimes people forget to include like these little branches. You got to get them all. Otherwise, it's not a full graph. So 1 over x looks like this. It's got 4 arrows. It's in 2 pieces. They always look like this. Okay, let's fill in the remaining critical information about this. I'm going to zoom in a little. So the x-intercepts, this is where it would intercept the x-axis. There's none. Still. Because you're not crossing that green line at this point. We do have some y-intercepts now. So how do you find y-intercepts? Well, just like any function, you compute f of 0, which means plug in 0. So 1 over 0 minus 2, that's just negative 1/2. So I'm going to write the y-intercepts as a point, and it's going to be 0, negative 1/2. I think it's just nice to start writing these as points. That's going to give us a nice point on our graph as well. So I'll just draw an arrow right there. That's a point that we also get on our graph. Vertical asymptotes. Well, it would have been at 0, and it's shifted over to 2, so we're going to say it's at x equals 2. And the horizontal asymptotes are still at y equals 0. We didn't have any kind of any kind of vertical shifts. And now let's take a look at the second one, negative 1 over x plus 1 plus 2. So this one has 3 transformations. There's this x plus 1, there's this negative 1, and then there's this plus 2. So it's going to go in the order that all transformations go. We're going to do our x transformations first. So the plus 1 is going to make this go left 1. This negative 1 is on top. It's not attached to the x. So this is like a y transformation. So this is going to reflect, how do you spell that? The graph over the x-axis. And then the plus 2 is going to make everything go up 2. So we are actually ready now to go ahead and graph this. We're going to do our vertical asymptote first. We're going to go left 1. So that's going to be at -1 now. I'm actually going to draw the asymptote next. That is up 2. So we were at 0. Now it's going to go up to 2. So the asymptotes are crossing at -1, 2. And because this was reflected over x, it previously looked like this. It's now going to be reflected over the x-axis, so it's going to look like this instead. And I'm going to fit all of those points into the asymptotes. So this is going to go to the point, we're at -1, 2. So this is going to be -2, 3. And this point here is going to be 0, 1. And these are the 2 points the graph has to go through. So now we'll sketch and finish off the graph. Just like that. Not so bad. Now, there's a couple of values we need to find. Let's do the vertical and horizontal asymptotes first because we already kind of listed them. The vertical asymptote is going to be x equals -1. The horizontal asymptote is going to be y equals 2. We moved up 2. The y-intercept, we already kind of found from the graph. It's 0, 1, but we could also plug in 0. So -1 over 0 plus 1 plus 2 is going to be 2 minus 1, which is 1. So this is going to be, again, 0, 1. Which we knew, but we could have used that as a way to check, or as a way to kind of tell where our graph's going to live. Now, we can't actually find the x-intercept. I know it's somewhere in between 0 and 1, but we can do better. So let's look at finding the x-intercepts. When you want to find the x-intercepts, you set the graph, the equation, equal to 0. You're letting y equal 0. So how do you solve that? Well, again, take a second and pause the video, see if you can do it. But if you don't feel like doing that, then just follow along. I'm just multiplying by -1 here to make everything positive because I had negatives on both sides. And I'm going to clear out the fraction. So now I've set that equal to 0, and I know that when x is -1/2, y is 0, and that's the x-intercept of this graph. So when you're graphing rational functions, if you have something that is just an obvious transformation of 1 over x, please graph it like a transformation. It saves you a lot of energy and effort. That said, a lot of rational functions are not just transformations of 1 over x, or it's not entirely clear how the transformation worked. So in that case, we have a lot of other techniques that we can do. And I actually first want to just take a look at a rational function that's been graphed on Desmos and make sure you understand what the different parts are because we're going to be talking a lot about the different parts. So here's the equation of this rational function. Here is its graph. We are going to label the holes, the intercepts, and the asymptotes just on the graph. So the first question is holes, what? That was something that didn't happen with the transformation of 1 over x, is what these holes are. And a hole is a piece of the graph where the graph just skips over a single point. And we often write that with a big open dot in the middle of the graph. It's a point that's not in the domain of the graph. So the hole on this graph is right here. I'm just going to label this hole. And we'll talk about how to find the exact location of these holes in just a minute. Let's finish labeling the graph. The other pieces that we can see are the intercepts. So again, the x-intercept is where it intercepts the x-axis. The y-intercept is where the graph intercepts the y-axis. We'll say y-int for intercept. We have the vertical asymptote. That's the vertical line. So we'll call this the vertical asymptote. That is often abbreviated VA, but that doesn't excuse you from spelling both of these words correctly. That's a really difficult spelling test. And then we also have the horizontal asymptote. Again, often abbreviated HA, but you should be able to spell both those words and know what HA means. And again, just to be clear, the asymptotes are not part of the graph. They're kind of like guidelines that show where the graph goes and where the graph doesn't go, what lines it might cross, what lines it might not cross, but they're not actually part of the graph. The parts of the graph are the black line here. That's the actual equation. The asymptotes are just the things that kind of define its shape. So these are the main 5 things, the intercepts, asymptotes, and holes. They're going to tell us where graphs live. So this graph we can see has a hole at 3, -3. So holes always have coordinates. They're not just floating out in space. They have coordinates. How do you find it? And in a rational function, what makes a hole? Well, when you have a rational function, so I'm going to copy this equation over. When you have a rational function and you have a common factor on the top and bottom, so it has to be factored, and this one came to us factored, but we might have had to factor it out, you can cancel that common factor. But before you do, you notice that we don't want to divide by 0, right? So if we plug in 3 here, then we know we'd be dividing by 0. So we say, when we look at this, we say, well, x cannot be 3. And that could make a vertical asymptote, or it could make a hole. How do we know? Well, we know because there's a common factor on the top and bottom, so these are going to cross out. So we're going to have, at x equals 3, we're going to have a hole. But we don't just want to write hole at x equals 3, because then I might be tempted to just put the hole right here, where it doesn't actually seem like it's part of the graph. So instead what we're going to do is rewrite this in reduced form. We cross this out, so then this is turned into negative x plus 3 over x minus 1. And now that we crossed out this term that would cause division by 0 if we plugged in 3, we can now plug in the x value to get the y value of the hole. So I'm going to do that now. So then this actually says that we're going to have a hole at 3 and -3. So we had to cancel the factor, identify that we're going to get a hole at 3, then we're going to plug 3 into the reduced version, and we get the y value of the hole by plugging that in. And we can see that the coordinates of this are indeed 3, -3. So that's how you create holes. I always like to find those first because it also lets us simplify the equation. And once we've crossed out those holes, we know where they are, we put them on the graph, we can now work with the simplified version, and it's usually going to make life a lot easier. In fact, while we're on this page, we can find the y-intercepts. Now we already can see where the y-intercept probably is, but I want to show you doing it here because we can use the reduced version. So again, to find the y-intercept, we plug in 0. But we can use that reduced version, so it's going to be -0 plus 3 over 0 minus 1. I don't have to worry about the -3, -3. Those would just reduce out anyway. And so you get -3 over -1, or 3. So the y-intercept is going to be 0, 3. So if we were making this graph, we'd already have some places where we know the graph is going to be, even though we haven't even thought about the asymptotes yet. We know the holes, we know the intercepts. A really important feature of these rational graphs are the x-intercepts. Just like in any other graph, you need to know where the zeros are. Those are some of the main features you're interested in. And for rational functions, the x-intercepts are always going to be at the zeros of the numerator. The numerator is the top. It's not a fraction, by the way. This is just here. It's just a box. So if this is my reduced version, and again, I'm using the version that I've reduced out any terms that created holes, I'm just looking at this, the zeros of the numerator are just going to be what makes those factors 0. So in this case, x equals -3 makes the factor x plus 3 equals 0. So we're going to have an x-intercept at x equals -3. So the x-intercept will be y equals 0. I'm like, right, let's just check it out. Let's plug that in. So it'd be -3 plus 3 over -3 minus 1. Oh my gosh, it's 0 on top. -4 on the bottom, it doesn't even matter. That's just 0. So that's why the zeros of the numerator cause that, is they just make the whole fraction 0. So that's how you find your x-intercepts. They're easy. They're the zeros of the numerator. So our x-intercept is going to be -3 and 0, which you can see on the graph right here, -3, 0. Again, we're not like graphing yet. I'm just referring back to this one. We will eventually make our own graphs. We're just looking at all the tests. So we know the x-intercepts. What about the vertical asymptotes? Well, those are anything where the function is undefined that's not a hole. So we're going to say undefined, but not holes. And that's going to be at the zeros of the denominator. So for these vertical asymptotes, again, I'm using the reduced version. I already got rid of the holes. And now I'm just looking at the denominator, and I notice that x minus 1 is in the denominator. So I need to get that factor equal to 0. So I need x to equal 1 will be a vertical asymptote, or VA. And that's it. And let's go look at the graph again. Oh my gosh, our vertical asymptote is indeed at x equals 1 right here. And again, remember, it's a vertical line. So we've got our x-intercepts, we've got our vertical asymptotes, we've got our hole, we've got our y-intercept. How the heck do we find this horizontal asymptote at -1? You know, in the previous example here, we just had an obvious shift value. It was +2 and the asymptote was 2. Here, there's not an obvious shift value. There's not an there it is. There's not an obvious shift value. There's not an obvious -1. This is kind of the weirdest thing. Here's how you do it. There is a test. So here's the test for finding horizontal asymptotes for any rational function. I want you to remember that rational functions are fractions of polynomials. So you have like a numerator, p of x, and a denominator, which we can call q of x. And each of these is going to be a polynomial, so each of these has a degree. So there's a lot of possibilities for this degree, but the test is the relationship of the degrees. So if the degree of the numerator and denominator are equal, I'm not going to be able to use this. We'll just keep writing. If the degree of the numerator and denominator are equal, the horizontal asymptote is the ratio of the leading coefficients of P and Q. And that's actually the case that we had over there. So we had negative x plus 3 over x minus 1. Well, this is a first degree, and this is a first degree. So these have equal degree. So the leading coefficient of the top is -1, and the leading coefficient of the bottom is +1. So the horizontal asymptote by this test is -1 over 1, which is just -1. So the horizontal asymptote is at y equals -1. And we can go and flip and take a look. Oh, where is it? There's our graph of this function, and oh my gosh, it is at y equals -1. So that's because the degrees of the top and bottom were equal. And even in the original, before we canceled out that whole, froze a little bit, we could have seen the degrees were equal. This is, degree 2 divided by degree 2. So we'd be looking at the ratio of the leading coefficients, -1 to 1. Now, the other case that you might see today is if the degree of the bottom is greater. There's more exponents on the bottom. So here, we'll just make a new space. So we'll say if the degree of the denominator is more than the degree of the numerator, then all you have to do is say that the horizontal asymptote is at y equals 0. So an example of this would be, well, 1 over x, right? This is degree 0 over degree 1. That's y equals 0. But it could also be something like x squared minus 3x plus 5 over x to the 4th minus 2x plus 1. The degree of the denominator is higher than the degree of the numerator. So if you think about that carefully, as x gets very large, which is what these asymptotes are all about, the denominator is going to get bigger faster. And if the denominator gets bigger faster, then it's got to trend towards 0. So we call these sometimes bottom heavy. Functions. And that tells us when our horizontal asymptote is y equals 0. There is a third part to this test, which is if the function is top heavy. And we're going to cover that in another video, not today. We're going to stick with just these two kind of horizontal asymptotes, either 0 or if the degrees are equal, it's the ratio of the coefficients. We're about to do a couple examples, but as we do them, we're going to go through this process really quickly. So I'm going to recap what the process is for graphing a rational function. The first thing you do is you look at the equation, and step 0 is if it needs to be factored, you factor that thing all the way out. This one came to us factored, so we didn't have to factor anything. Then you look for any common factors on the top and bottom, cross those out, and those are the locations of your holes. And you plot your holes. Then you plug in 0 and find the y-intercept. That's the next thing. Then you look at the zeros of the numerator. Those are going to be your x-intercepts. You look at the zeros of the denominator. Those are going to be your vertical asymptotes. Then you find the horizontal asymptotes by comparing the degrees of the top and bottom. And it's either going to be 0 or some other constant. You plot all those in, and then we're ready to make a graph. So let's go into the examples and actually look at what using all this to make a graph looks like. All right, there we go, folks. So on this example, I had to change my sheet a little bit. Your sheet should match now having a -3 on there instead of what it had before for me. So let's go ahead and graph this. The first move is we got to factor everything out. So the top is a 2 is going to come out, and that's going to be 2, and then x squared minus 1. That factors further, so it's going to be 2x plus 1, x minus 1. And the bottom we have x squared minus 2x minus 3. So we'd better have an x minus 3, because we have that minus 2, and then that's going to be an x plus 1. Again, so everything's factored out now. That's always going to be your first step. Step 2. Let's look for holes. So holes are going to be wherever there's a factor that cancels on the top and bottom. So that x equals x plus 1 cancels out. So we're going to have a hole at x equals -1. But it's not necessarily just going to be -1, 0. We got to figure out the y-coordinate of the hole. So what we're going to do is first rewrite this in its simplified version to x minus 1 over x minus 3. And then we're just going to plug in -1. So I'm going to do some space down here for scratch work. So it's going to be 2, -1 minus 1 over -1 minus 3. That's 2 times -2 over -4. Hey, that's -4 over -4. So that's 1. So the hole is going to be at x equals 1, y equals 1. X equals -1, y equals 1, which will be the point -1, 1. So I'm going to make a open circle there to represent the hole. And even though it's a hole in the graph is going to connect to the hole in some way. So it is actually kind of a useful point to have. Okay, We now have this simplified version, so we can find all the intercepts. Just making this a little larger. So the first intercept that we could find is when x is 0. That'll be the y-intercept, so then that's going to be 2 times negative 1 over negative 3. So that's going to be, looks like positive 2/3. So we're going to have an intercept at 0 and 2/3. And then when the numerator is 0, that's going to be the x-intercepts. So that's going to be 0 at x equals just 1. So it's going to be 1, 0. So we'll go ahead and plot those on. The x and y-intercept, 0, 2/3. So that's somewhere like right around here. And 1, 0. So that's somewhere right around here. Okay, now, again, this is not enough information to get the rest of our graph. We got to get some asymptotes going on. So, vertical asymptotes are from the zeros of the denominator. So that's going to be looking at that x minus 3. So we're going to have a vertical asymptote at x equals 3. Whatever would make the denominator 0, that's what we're looking at. And then horizontal asymptotes, we need to apply the test. Well, this is degree 1 over degree 1, so we're going to look at the ratio of coefficients. Well, the coefficient on the top is 2, and the coefficient on the bottom is, it's not written, but is 1. So it's horizontal asymptote at y equals 2 over 1, or y equals 2. I'm going to leave some space down here for my sign chart, because I still need to do some more work. But now we can start to fill in things on the graph. So our vertical asymptote is going to be at x equals 3. So just plot that in. Use a dashed line. You can use just a really light solid line also, like whatever works best for you. And at y equals 2 is the next part of our graph. Okay, so we're trying to figure out where this graph goes. Now I might have a guess that it probably does something like this. But what is going on over here? I don't know. And so to figure that out, we're going to use a sign chart. So the last piece of information that we can do is figure out where the graph is above 0 or below 0. This is what we did in section 2.7. So what we can try to do is try to solve the inequality 2x minus 1 over x minus 3 is greater than 0. And to do that, if you remember in that section, we made a little chart. We made a little number line, and on that number line, we put all the things that could be the boundary points where something could change sign. So this could change sign at 1 or 3, and that's it. Those are the only places that we can possibly change sign. And then we just needed to think about plug in test values in each of the regions on the graph. So there's 3 little spaces we need to kind of do some test values to figure out whether the graph is going to be positive, negative, 0 at those spots. So we actually already kind of got some test values over on this side, but we're just going to keep going as if we didn't have those. So let's think about 0. Well, if we plug in 0, then we'd have a negative term divided by another negative term. So I'm going to write that up here. So to the left of 1, we're always going to have a negative over a negative times 2, which is always positive. So that doesn't do anything. So we're going to have a positive. The graph is above the axis down here. Between 1 and 3, so that's like if we plugged in 2, well, the top is going to flip sign and become a positive, while the bottom stays negative. X, 2 minus 3 is still negative. So this is going to be a negative number. Positive over negative is negative. And then when we're above 3, both terms will always be positive. 4 minus 1 and 4 minus 3 are all positives. This would be like a positive over a positive, which would still be a positive. So this is telling us the net sign of our graph, where our graph lives. To the left of 1, our graph must live up here. To the right of 1, but not at 3, our graph must live down here. And then to the right of 3, our graph must live up here. And this actually gives us the information we need to complete the graph. I'm going to leave that highlighting in until the end, and I'll just clear it out at the end to kind of show what I'm connecting to the sign chart. So we did our plus minus plus that's showing us where the graph goes. So now we're ready to fill in. We're going to obey all our asymptotes. We're going to kind of connect these dots. And remember that these are still going to look like 1 over x. You want it to look like that. So we're going to start here at this point and go down. And as we approach the asymptote, we're going to shoot off to negative infinity. Then we're going to go through and hit these points. We're going to connect to the hole and then keep on going past the hole. And on the very far left, we're going to again put an arrow showing we're going off to infinity for the x and that the y is just approaching 2. Now, there we had some like really good points. Here we're just using the sign chart. We could also plug in a value. Like we could just plug in 4, and that's not a bad idea. In fact, why don't we do that? So let's just plug in 4. So it's going to be 2 times 4 minus 1 over 4 minus 3. So that's 6 over 1. So at 4, it's saying the graph is actually way up here off the page. And that means it's going to come down here and just stay between these asymptotes like this and not actually touch 0. I know, by the way, that this graph cannot do this. This is impossible, and the reason that's impossible is because if it did, there'd be an intercept there, and that would have shown up in the equation. But we know the only intercept is right here. So that's another clue about what the graph does on the right-hand side. So I'm going to get rid of this. I'm also going to clear out that highlighting because that's kind of in the way. And we can really see what this graph of this rational function should look like. Now, again, I know we got that 0.61. You don't have to be super specific about points for these. You want to get your asymptotes and your intercepts, and then everything, and your holes. And everything else you can just kind of fill in. It doesn't have to be super exact, at least for now. So that's what this looks like. I know it's a lot. Let's try another one. All right, so we're graphing x minus 1 over x minus 2, x plus 2. First thing we check for is holes, and there's no common factors that factor out, cancel out, so we're going to have no holes. That'll make things a little easier. Let's look at the intercepts. So the x-intercepts are when y is 0. That's going to be the zeros of the numerator. So we're going to have an x-intercept at 1, 0. So we'll go ahead and plot that right there. And we're going to have a y-intercept when we plug in 0. So that's going to be 0 minus 1 over 0 minus 2, 0 plus 2. You could probably do this in your head. It's negative 1 over negative 4. So that's 1/4. So we're going to have a y-intercept at 0 and 1/4. So we'll go ahead and put that in right there. And then clear that out to make some space. Vertical asymptotes, that's going to be the zeros of the denominator. So zeros of the denominator are 2, I'm going to write it as x equals 2 and negative 2. So we'll go ahead and put those in the graph. So that is here. And then horizontal asymptotes. Well, let's take a look. This is a degree 1 divided by a degree 2. There's 2 factors. So we're not going to look at the ratio of coefficients. We're just going to say that this is a horizontal asymptote of y equals 0. That's the second part of the 2-part test. So I'm going to go ahead and put that horizontal asymptote in right here. We're almost done. But we don't know what this graph does yet, so we suspect it's probably going to do... I mean, it's going to hit this point, and it's going to connect to this 0, so we know it's got to do this. But from here, could it bounce up? Could this come back up? Could it be like this? Could it be like this? But what if it's like this? Like, there's too many options. So how are we going to figure it out? We're going to use our little sign chart. So, let me recopy this equation down. So to make our sign chart, I'm going to make a little number line. And on the number line, we're not going to put every number. We're just going to put all the things that would make something 0 on here. So we're going to put 1, 2, and -2. And the sign chart's not to scale. It doesn't have to be. That doesn't matter. We're just using this to kind of figure out where the boundaries are. So now we actually have, with 3 numbers on the chart, so we have 1, 2, 3, 4 regions we need to check. So let's just start on the left. If we're less than -2, then all 3 factors would be negative, because it'd be, the factors of subtraction will be negative, and then something less than -2 plus 2, negative, and negative. So we have 3 negatives. 3 negatives makes a net negative. Between -2 and 1, like 0, well, we know when we plugged in 0, we got a positive. But we could also think about, we've crossed over this -2, so this factor is going to turn positive now. So we're going to have a negative, and a positive, so that's going to be a net positive. When we cross over 1, so somewhere between 1 and 2, you can think about like 1.5, maybe, if that helps to plug in. You don't actually have to plug in 1.5. Anything more than 1 will give you a positive on top, and then divide by something that will be positive on the bottom and negative on the bottom. So then this is going to be a net negative. And when you're more than 2, all 3 of these factors will all be positive. So this is going to be a positive over a positive, which gives you a positive. So at every one of these little boundary points, the graph is going to change sign. Negative, positive, negative, positive. So let's highlight that in here and see what that tells us about the shape of the graph. Negative, positive up until 1, negative between 1 and 2, and then positive for the rest of its time. Now we know where the graph can live, and it has to look like a rational function, which means it has to fit between its asymptotes, it has to hit its zeros, and it can't cross that axis unless it's at one of those points we've already plotted. So all that together, get those back, gives us very few options. The graph pretty much has to look like this. We have to curve between the asymptotes here. We have to come from this asymptote, over here, cross our 2 points, and go down. That looks a little vertical, but we're just sketching, so it's okay. And then we have to be positive here, so it's going to look something like this. Again, not actually crossing that 0 line. I am going to clean this one up a little bit. That's just a little too vertical, so it probably goes like a little more like this. Okay, that's a little better. And we'll clean this highlighting up because that's not part of the graph. There it is, the graph of a rational function with, oh my gosh, 2 vertical asymptotes. And that was the last thing I wanted to share with you is we've been spending today looking at transformations of 1 over x, but not all rational functions are that. They can have any number of vertical asymptotes. They're only going to have 1 horizontal asymptote. That's always the same, either this one single line left and right, but you can have any number of verticals. All right, folks, that's it. That's all I've got for you today. So we're going to leave it here. Enjoy your classwork, and I'll see you all next time.